What is going on, Algebra Bros? It's Mr. C here. In this video, we're going to analyze the graph of a polynomial function. The function we're going to be using is somewhat of a partially factored form of f of x. And in step 1, we're actually going to want to multiply everything out to get the standard form because they're requesting us to determine the end behavior of the function's graph. So without further ado, let's go ahead and multiply a couple of these factors out. I recommend doing these two first to get x squared times x squared minus 4, and then clearing parentheses to get x to the fourth minus 4x squared. Now the reason why we need the standard form is because end behavior is dictated by the leading term, which the leading term in this case is x to the fourth. Now the thing about x to the fourth is that it has an even degree and a positive leading coefficient. Now in my math lab, it'll probably request the power function, that blah blah blah, and x to the fourth would be your answer for that. But in terms of a visual of end behavior, because the leading coefficient is positive and the degree is even, we're going to have one end pointing up in quadrant 1 and the other end pointing up in quadrant 2. So that would be the end behavior, or EB for short. Now to find the x and y intercepts, starting with the x-intercepts, we want to solve the equation f of x equals 0. And here I'll use that partially factored form, even though we FOILed it all out in the step 1. The reason why for the factored form is because it's a little easier to solve for x when the polynomial is in factored form. And when we solve for x in a situation like this, we will be finding the real zeros, which indicates the x-intercepts as we saw in that ring of results from the last section. Now, I'm gonna rewrite x squared as x times x to help us out with step 3. And of course, what you would do is you would set each factor to 0 and solve for x where necessary. So it looks like 0, 0 is an x-intercept. So it's -2, 0, as well as 2, 0. Okay, no need to write a duplicate 0, 0. So these will be our x-intercepts. As for a y-intercept, to figure this out, we plug 0 into the function. And if you use the factored, well, partially factored form version, that's 0 squared times 2 times -2, and all that zeros out. So the y-intercept is at 0, 0. Now, with step 3, it says determine the zeros of the function and their multiplicity. And then we'll move on to determine whether the graph crosses or touches the x-axis at those x-intercepts. So we actually have the zeros already solved for. One of the zeros is x equals 0, another is -2, and the third and final is +2. Now if you look at how many times 0 showed up as an answer, it showed up twice. So 0 would have a multiplicity of 2, or I'll say mult2 for short. -2 shows up one time, so that would have a multiplicity of 1. And then +2 also shows up one time, therefore it would have a multiplicity of 1 as well. Now as for whether the graph crosses or touches the x-axis at these zeros or x-intercepts, note that 0 has an even multiplicity, and zeros of even multiplicity cause the graph to touch the x-axis at the x-intercept. So I'll say touches x-axis. And any zeros of odd multiplicity, such as -2 and +2, they will cause the graph to cross the x-axis. All right, and that's how you take care of step 3. So we're seeing it all come together here. Step 4, so use a graphing utility to graph the function. All this basically means is we'll enter the function into our graphing calculator, and it might be easier to use the standard form of the polynomial when doing this. And the reason for graphing this in the graphing calculator is to not only confirm some of our algebra work, but to also approximate the turning points of the graph. And do recall that turning points are basically your maximums and minimums. So I'm going to go ahead and get my calculator out. Type in x to the 4th minus 4x squared. And we'll do a window adjustment here. If you look at the coordinate plane a little further down the page, it goes from -5 to +5 along the x-axis as well as the y-axis. Okay, so it looks like there are 3 turning points. We've got one in quadrant 3. One looks like it's at the origin, and another one in quadrant 4. So just a recap as to why where did my notes go? There we go. Okay. So our graph looks a little something like this. Actually, you know what? Put it over here. That's a rough sketch of our graph, and the reason why those are turning points is because as you trace this graph from left to right, it decreases until it gets to this absolute minimum, also a local, and then it increases until it gets to what looks like a local maximum, in which case it decreases till it gets to a second absolute minimum, doubling up as a local, and then it increases from there on out. So each one of these points at which the graph changes behavior is a turning point, and as you heard me describing, they're also maximums and minimums. So hence the reason why we would want to find the maximums and minimums. I'll demonstrate one of the minimums and then leave it up to you to find the rest of the turning points. And I'm going to find the minimum that's in quadrant 3. I'll do second trace, option 3. Scooch over to the left-hand side of the valley. We'll go over to the right-hand side for a right bound. And then we'll go near the point for our guess. And to 2 decimal places, we're looking at roughly -1.41, comma, -4. And that would actually be an absolute minimum, doubling up as a local. The other one, which I'll have you confirm on your own, is at 1.41, comma, -4. And then there's a local max, which I'll have you confirm as well, at the origin. So with all this in mind, let's go ahead and translate this information into the coordinate plane. We had x-intercepts at -2, 0, and +2. And we also have turning points at those that we just found in step 5. All right, and we saw the shape of the graph. We have ends pointing up, which confirms our end behavior from step 1. Okay, even degree, positive leading coefficient. Okay, those ends both point up. And there it is. Okay, so we plotted the x-intercepts, the turning points, and then we used all these points to help us connect, as well as with a little bit of assistance from the graphing calculator. Now, as for the domain, keep in mind the domain of any polynomial function is all real numbers. So just memorizing that fact will help you answer that real quickly. The smallest y value on this graph comes from these absolute minimums, and that's -4. Then anything beyond -4, going up to positive infinity, will also be a y value on the graph. Now, as you go from left to right on this graph, starting at the left end, the graph decreases at first, as we saw a little bit earlier. And that's going to decrease all the way from negative infinity to negative 1.414. I'm sorry, negative 1.41. And then it increases from the absolute minimum to the local max, and that happens between the x values of negative 1.41, comma 0. And then it decreases from the local max to the second absolute min, which that's between the x values of 0 and 1.41. And then it increases from there on out, meaning that the part of the x-axis from 1.41 to positive infinity consists of x values for which the graph is increasing. And there we have it. We've analyzed the graph of a polynomial function. Please let me know if you have any questions. Otherwise, thanks for watching, and I'll see you next time.